So, last class we have discussed if you have a actual plant transfer function is g of s and the plant model g m of s, and there is a discrepancy between the actual plant and the plant model, and the controller is designed based on this model, plant model. Now, our question is whether the design controller based on the plant model, whether it will be able to stabilize the part of model, that whatever the discrepancy between this and this, that are compensated with a part of model. And if it is able to withstand the stability of this system, then we have to find out how big that perturbation is there just before becoming the system is unstable, find out that big how big that perturbation is there. So, if you recollect this one, we did it that this is the plant model, this is the controller. Controller is designed based on the plant model, and the discrepancy between the plant actual plant and plant model we have compensated with a delta A, which is connected across the plant. So, this is nothing but a additive in the sense whatever the plant model is there, with the plant model the perturbation model is added. We have made an assumption that delta S is A is stable one. One can find out the maximum upper or upper bound of delta A with the knowledge of plant model and actual system frequency response and plant model frequency response. From that you can find out the upper bound of delta A. Anyway, so how to study the stability of this system in presence of that controller, and controller is designed in presence of that in considering the plant model. So, you take that input to the output of the part of model is V and input to the part of model is U. So, you take out this block and find out the transfer function between the input V and the output U, and that we have found out that transfer function is m of s, that transfer function is m of s. And by using the small gain theorem, we have to see whether the system is stable. If it is stable, what is the how big the perturbation is there just before it's become unstable. So, if you look at this one, that small gain theorem we have applied, and we found out the that upper bound of delta A is less than that mod of that what C j, this is a controller transfer function, and S j is sensitive function. This delta A must be less than this one. So long this condition is satisfied, the design controller will be able to stabilize the part of plant, and that design controller is based on the plant model. But I already mentioned this provides you the what is called conservative results. It means that if there is a perturbation, but this condition is not satisfied, it does not mean the system will not be stable, it may be a stable one. So, that is why it is given. Next we consider the multiplicative perturbations. So, the perturbation before the plant model, and this is this, and delta m is the multiplication, m stands for multiplicative, a stands for additive. So, this transfer function is, if you equivalent block is that 1 plus delta m. So, if you see the total block of that one, this transfer function g m into 1 plus delta m s. So, it is a multiplicative, that two transfer functions. So, actual plant is model plant per multiplied by part of model with 1. So, again in order to study the stability of this system in presence of multiplicative uncertainties, then what you have to do, mind it that CFOS is designed based on the plant model. Then there is a perturbation, I want to check it whether the system will be stable or not under that perturbation, and that perturbation is multiplicative perturbations. And in order to find out this one, you take out the block of that one perturb block, that means output of the perturb block is V, input to the perturb block is U. So, you take it out, find out the transfer function between the input V and the output U after taking out. So, again once again we got the that m of s is nothing but a that what is called, this is the output, this is u of s, sorry, it is not a u of s by V s, this one, the transfer function will be denoted by m of s. So, this nothing but a this. Okay. And now, look at this one, this is the sensitivity function, sensitivity function is that one, not this one, this is the sensitivity function, the T 0 of s. Complementary sensitivity function is h 0 and complementary sensitivity T of T 0 of s, this is the complementary. So, u s by V s is equal to that T 0, this C 0 is not there, T 0 this one, but G m, you see this one from here to here the transfer function V s to y s, G m 1 plus G f is, I am sorry, this is a y s, this is y s, sorry, and when we are, this is the y s, when you are finding m s is nothing but a input signal, that output signal, this is T s. So, now in order to find out the transfer function of Perturbed, you have to again push it the Perturbed model delta of m. Now, find using the small gain theorem, this is the condition we have arrived, this C s is not there. Okay. So, again this yields the conservative results, that is what we have studied it. Now, next is we have considered a general control configuration with uncertainty. Okay. That means, let us see, we have a mass, then you have a damper and spring, and the force is applied F of t. Now, this m 0, k 0, b 0 is the nominal parameters, the model of the mass, spring and this, and actual actual mass, this is something else. So, that we are compensated with a delta A m, delta A b, delta A k. So, we have considered additive perturbation, and k stands for spring, b stands for damping and m stands for mass. So, this is the dynamic equation of this one, and f is the forcing function or input to the systems. So, naturally that when you give an input, the before it comes to steady state, there will be a dynamics is involved this one, and dynamic equation is described by this one. So, this thing I can easily convert into our main aim to take out delta A m, delta m, delta A b, delta A k from the plant model, separate this from this model. So, we define the state variable, x is the displacement, x dot is the velocity, x double dot is the acceleration. So, displacement of the object is x 1, new state variable x dot is equal to x 2 dot x 2, which is nothing but x 1 dot. Now, from equation 1, from this equation 1, I can easily write that expression, if you see this one. So, this I am now representing into a block diagram form. If you see this block diagram, x 2 dot is nothing but a x 1 multiplied by this, x 2 multiplied by this, and forcing function divided by some quantity 1 by m 0 by delta m. So, x 2 dot, so we have, this is the second order systems. If you see the second order differential equation, we need to realize in state space model for two first order differential equations. So, we consider this is our x 2 dot, which output is your x 1 x 2, which is nothing but a x 1 dot, and again you put it integrated, this is x. So, if you see x 1 multiplied by delta k, k 0 plus delta A k, x 1 multiplied delta A k, this one. So, this block is nothing but a, this block is nothing but a that one. Then x 2 multiplied by b 0 plus delta b. So, this combination is nothing but a that one. So, these two terms already we got it, this and this term, and L f of t. So, this two signal is coming and going here. So, this is not a that one, that means I have told you that x 1 dot is equal to x 2, that is you do not consider that this is a your x 2 dot. So, this signal is nothing but this signal plus this signal, and then f t plus f t, that is the f t. So, that whole thing will be divided by that 1 by m delta m 0, 1 by delta m 0 is this block. If you see from here to here transfer function, it will be 1 by m 0 delta m, which I have shown it here. Okay. So, this is the block representation of that one in state space model. Next is our job is how to write the state space model of this one. So, we have seen this is a second order mass damper and this is a second order system. There will be a two state variable, one is x 1, x 2. Physical meaning of x 1 is a displacement x and x 2 is the velocity and x 2 dot is the accelerations. So, now we can write it this block diagram representation. If you see that one, I am not drawing once again this one, but we are telling it that let us call this signal is I am denoted by z 1 of t. Then output of part of model, what is this one, that is d 1. Similarly, this signal what you are getting it here, that is z 2 t, and output of that signal, that output of this signal is d 2. Similarly, this signal I am considering z 3 of t and this output of that signal is d 3. So, now I am just writing the state space equation from this block diagram, nothing else. So, if you look that one, you see if you look that one, I can write it, what is our x 1 dot, this x 1 dot. X 1 dot is what? X 1 dot is nothing but a your x 2. You see x 1 dot is nothing but a x 2. So, if I write this expression x 1 dot of t is nothing but our x 2. So, x 1 of t, x 2 of t and 0 and 1. There is no other terms involved in this equation, x 1 into 0, x 2 0 plus there are, we will write this thing, there is no other terms is there in here for the time being. Now, x 2 dot, see this one x 2 dot, x 2 dot is what? See x 2 dot, this signal add together, then this signal passing through this one is x 2. So, it is nothing but a, if you see x 1 into k 0, one signal is going x 1 into k 0, this only this signal I am considering x 1 in k 0 going this way divided by this one, agree, passing through this one, that 1 by m 0. So, this is going here, coming here, going here, then passing through, let us call with this block. So, I can write it x 2 dot of t is nothing but a, so x 1 1 by m 0. So, it is a minus, why minus is considering, that minus sign is that signal is going with minus sign, agree. So, this is a minus k 0 by m 0. Now, this is a x 2, you see this is the x 2, x 2 b 0 going this signal minus sign and 1 by m 0. So, this is k b 0 m 0 x 2. This is not, there are some other signals also there in x 2. Now, coming to the perturbation side, x 1 multiplied by delta a k. What is this output? That output is d 3. So, d 3 is coming this way minus sign again m by 1 by m 0. So, I can write it d 1, d 2, d 3. Agree? I can write d 1, d 2, d 3. So, if you consider d 3 this one, d 3 this x 2 x 1 multiplied by delta x 1 is equal to d 3, d 3 going this way, d 3 going this way, agree, multiplied by 1 by m 0. So, it will be minus 1 by m 0. Now, d 2 you see x 2 multiplied by delta a key is d 2, then going like this way, in this one minus multiplied by 1 by s. So, minus sign is there. So, it is a d 2. So, it will be a minus 1 by m 0. Similarly, d 1 is going like this way of m 0, this minus m 0. So, it is a minus 1 by m 0. So, and other terms is not there. So, this is 0, 0, 0. Okay. So, what is left? Only left is signal is f. F is going and this is multiplied by f 0. You see f is going multiplied by 1 by m 0. So, this term is coming where? It is associated with the x 2 dot. So, it will come plus 0 1 by m 0 into f of t. See this one, f of t multiplied by 1 by m 0 and that signal is coming here. So, x 2 dot is combination of second, that is second row is combination of all these signals is x 2 dot. So, we can consider this is our forcing function means u of t. I can consider this is a matrix at and this is the state x of t and this is our denote this is our B of 1 matrix and this is our W of t, that is our disturbance or part of model output, and this is our, we consider this vector is our B 2 of t and this is nothing but a x dot of t. So, this is we have written it for this one. So, let us call this is equation number 1. Then further we can write it, you see the expression of Z 1. Z 1 is how related to it d 1, how related to Z 1 is nothing but a, if you see this one Z 1 multiplied by delta A m, agree, and Z 1 is what? Is nothing but a x 2 dot. Z 1 is nothing but a x 2 dot. So, I can write it Z 1 expression you same as the x 2 dot expressions, this one. This is nothing but our Z 1 of t, if you see. So, if I write the that signals Z 1 of t, Z 2 of t, Z 3 of t, we can write it this into state form in express in terms of the state, in terms of part of model output, and the input. We will fill up this thing and which is nothing but a u of t. Now, Z 2 is nothing but our, if you see x 2 dot and x 2 dot we got it this one, you just filled up like this way. So, what is that one? Minus x 0 m 0 minus B 0 m 0 and this is minus 1 by m 0 minus 1 by m 0 minus 1 by m 0. So, Z 1 is nothing but a x 1 into this plus x 2 is this d 1 into this, d 2 is this and d 3 into this what we got it that one, plus one term is there z 1 which is equal to 1 by, you see this term is there 1 by m 0 f of t, 1 by m 0 f of t. Agree? So, this is why I have written z 1. What is z 2? See this expression, z 2 is what? Is nothing but a, z 2 is nothing but a x 2. So, what will write it? Z 2 is nothing but a x 2. So, you will write it simply 0, 1, other thing is 0, 0, 0, agree, and this is 0. So, this is our Z 2. What is Z 3? Z 3, sorry, Z 3 is, you see Z 3 is x 1, Z 3 is nothing but a, Z 3 is nothing but a your x 1, Z 3 nothing but a x 1. So, Z 3 is x 1 means 1, 0, 0, 0, 0, 0. So, this is we have expressed the part of model output a relation between the what is called Z 1, Z 2, Z 3 expression like this way. What is the main purpose of writing this one? I will tell you later, but this is we can write it this one. So, what is this one? I will write it now. This is nothing but our, if you see this is nothing but our x 2 and this is nothing but our x 1. So, we consider this is our C 1 and this is our x of t and this is our d 1 1 and this is our w of t or in general, that is d 1 2 and this is u of t, that this is a u of t. Then another equation we can write output equation. What is our output? If we consider the output of our system is x 1, this is our output, let us call this multiplied by 1 is our output. If this is the output, we will write the output equation y e t is the output equal to x 1, which you can write it is equal to C 2 x of t in general expression d 2 1 w of t d 2 2 u of t. In our case, this term is 0, d 2 1 0 and d 2 2 is 0, but in general structure I can write it like this way. In our case, this is equal to 0, this equal to 0 and C 2 in our case is 1 0, this is our C 2 in our case. So, in general structure is like this way now. I can write the general structure of any part of model, all these things we can, if it is additive perturbations is there, we can easily take out the perturbation model, perturbation term from the model. Agree? So, our state equation in general we can write it in general x dot of t is equal to a x of t plus b 1 of w of t plus b 2 of u of t and z of t is equal to C 1 of x of t plus d 1 1 w of t plus d 1 2 u of t plus y of t is equal to C 2 x of t plus d 2 1 w of t plus d 2 2 u of t. So, now I am telling this is x is a state vector, x is a, this equation is called state equation and x is a state vector whose dimension is, I am writing this dimension is let us call this dimension is n cross 1, n cross 1, and this is our exogenous or you can write it, this is the our input. What input? Part of system input. So, our you can write it this exogenous input or signal. This is the input signal. Okay. And this is the regulated output. This is the regulated output and this is the measured output. And this is the structure of, as I mentioned, a general structure of control problem. If there is a perturbation, all these things there, plant perturbation, all this, I can write it into this structure of this one. Now, see this one, what so this dimension, let us call the exogenous input dimension is p cross 1 and input dimension is m cross 1. Once I define the exogenous input, agree, and that this the input is m cross 1, that is m cross 1 and this is p cross 1 of this one, let us call. Then immediately I can find out this dimension immediately, but let us call these dimensions is p 1 cross 1 and p 2 cross 1, this dimension, or you better you just put it is m 1 cross m 2 cross input. This is input, this is also input, but this is the exogenous input. With this input we do not have any control. You see, in our case this is D 1, D 2, D 3. So, this is the output of the perturb plant. We do not have any control with this input, agree, to the plant, that is D 1, D 2, D 3. So, that is why it is exogenous input and this is the input signal which we can generate this control action, and that regulated output is P 1 cross 1 and measured output P 2 cross 1. And once you give this dimension, all matrices dimension is fixed now. So, it is the general structure of that one. So, now we are going to what is called the structure P delta form, structured P delta m. So, now if we conclude this one, you see, if you recollect this one, our actual system was, this is our actual spring mass damper systems and nominal plant is m 0, k 0 and b 0, and since there is a discrepancy between the actual plant and the plant model. So, this discrepancy is compensated by perturb model, additive perturb model, and that system we can represent into a this structure form, where W is D 1, D 2, D 3, and what is D 2, D 1, D 2, D 3 is nothing but the output of the perturb model, D 1, D 2, D 3, that is we have seen it. So, in general any physical system is given, we can express into this form. One is state equation, one is regulated output, we will more tell about the regulated output later, and is a measured output, where this output will be used for control to generate the control action, that means U, and this is the regulated output, that means we want to regulate the state, the error vector, agree, then we have to control the control signal, we have to controlled signal, we have to control, then this, that is why it is called regulated signal, controlled signal. Some signals we have to control it, but all these things Z is direct effect of this exogenous input, and exogenous input are such input which we do not have any control, such as the sensor noise and your that external disturbance and your what is called the command input, command signal, that is our exogenous input. Sensor signal, sensor noise, disturbances and command input generally we consider as a exogenous input. And regulated output is what? As I mentioned, state, error state vector, then your control signal, controlled signal, mind it, the signal which are going to control the signal. This so, we are now talking about the structured signal, that what is the model we got it, this one, how we can describe this in transfer function model form. So, this model you see, look what I am doing it here. So, I am representing the state space model of that system again into a 4 block representation. This is, you can calculate 4 block representation. So, we have a PM model, this one P11, P12, P21, P22, and we have a input. Now, let us say how many inputs are there? There are 2 inputs, one is exogenous input, another is your input signal. And how many outputs are there? 2 outputs, regulated output and the measured output, which will be used for our control purpose. So, naturally I can show it into 2 inputs, 2 output systems. This is our Z, this is our Y, you can say Y, and this is our exogenous input and this is our control input U of t. And this Q of t, I told you Y of t is used for control purpose, designing a to get a control signal, that let us call K of S is the controller. The measured output is used for generating the control signal U of t. In terms of this, you count it time this. Then you see there is a perturbation is associated What is W? In our example, if you see the W is what? If you see this is D1, D2, D3 is equal to our W. How they are related? If you see how they are related, if you see this expression, how D1 is related, Z into delta A m, Z1 into delta m is D1, Z2 into delta A b is D2, Z3 into delta A k is D3. So, we can, if you see this one for our example, we can write it, that expression from the figure itself, Z1 is equal to delta A m into D1 is equal to Z m into delta 1, D2 is equal to delta A b into Z2, D3 is equal to delta A k into Z3. Agree? Now, this thing you see how we can write it, D1 vector from your D2, D3 I can write is delta A m, delta A b and delta A k multiplied by Z 1, Z 2, Z 3, which can be written as that is nothing but a d, which is nothing but a w, is equal to delta A. This is I denoted, this is all elements are 0, this is 3 by 3, dimension is 3 by 3, is this, that I denoted by a, this matrix I denoted by a diagonal matrix which is denoted by delta A. Delta A into that Z, that is I denoted Z into Z, and that is I denoted with a d, which is nothing but a is equal to w I denoted. So, now see this one. So, what is you can think of it delta A multiplied by Z. So, it is acting as a input, then output is the part of model output is the. So, now ultimately you see the state space equation what we got it from there delta A is taken out. So, our plant model is now in transfer function domain, it is a that one. This whole thing equivalently I can represent by this one. Then how to find out that P 11, P 12, P 12, P 22? That is next question. Then how to find out this one? So, easily you can find out from the knowledge of that things. How will you find out P 11? See this one P m. If you consider the P m, just I am writing P m. P m is what? P m is P 11, P 12, sorry P 21, P 12, P 22. Agree? And what is this input? Input is that is in transfer function form. Input is W u, Z this. So, your transfer function you can say, then I can write it now Z of s, Y of s is nothing but a your P 11 of s, P 12 of s, P 21 of s, P 22 of s into the your input W of s and U of s. How, what is P 11 of s? Experimentally I can find out P 11 s. I do not excite with a input, okay? I give it the excitation with this one. Then what will be the Z? Z1, if you see this has a two parts, P 11 s into W of s plus P 12 s U of s, it is a Z of s, and Y of s is equal to what is this? P 21 of s W of s, P 22 s U of s. So, how to find out P 11 of s? You excite with only U of s, assume U of 0 is 0, then you will get it P 11 of s. Agree? You want get P 11 of s. Then how will you get it P 21 s? Because I excite with a W of s only, W U of s is 0. So, it will P 2 s is when you excite this one ratio of these two things, or y of y 1 of s is P 21 s, this I can get it this one. Similarly, P 12 s you excite only with U of s, then you will get it. So, from this one now I can write it what is P 1 of s. Can you tell me what will be the P 1 of s? P 1 of s you want to find U of s is U of s, U of t is 0. Okay. So, if you recollect this one, I am just telling you this. You see, suppose we have a system x dot is equal to a x plus b u. Say, I am just recall you, please recall this expression, how to find out the transfer function from the state space equation. How to find out the transfer function from the state space equation is the transfer function is g of s from state space equation to transfer function model. G of s is equal to c into s I minus a whole inverse b plus d. Agree? That is the transfer function. Same thing I will apply here. I will apply here to find out the transfer function of this one. You know already that this is a state space. I want to find out the transfer function of p 1 of s. Then what will the u of s is 0, means u of t is 0. U of t is 0, then what is this one? You will get u of t is 0, this is 0, this term will not be there, this term will not be there. So, between what? Between w and z is p of s. You see, between w and z will give p 1 of s. So, can you tell me what is the p 1 of s now from this one? Let us see from this one, p 1 of s. P 1 of s, p 1 s will be equal to, if you see this one, this is 0, this is 0. Now, between the state equation is there, output equation is this one regulated. So, what is our transfer function when this is not there, between these two things transfer function C 1. So, C 1, then S I minus a whole inverse, then b, b 1, then d, d 1. Then how to find out the again the what is called P 2 1 s. P 2 1 s the input signal W s and Y s is the output when U s 0. So, between state equation and this when U is 0. So, again I will write P 2 s is equal to C 2 S I minus a whole inverse, then your B 1, then your D 2 1, that is P 1. When this is means when u of t is equal to 0, these two quantities I can get it when u 2 is 0. Then I can find out P 1 2 s, P 2 2 s when w of t is equal to 0. Now, when w of t is 0, you see here I want to try P 2 1. So, this quantity w of t 0 means w s is 0, then I can find out the input is u s, output is z. So, what is P 2 what? Between the input is y, output is z when w is 0. So, how will you find out that one? Again P 1 2 is C 1 S I minus a whole inverse B 2 plus D 1 2 D 1 2. Similarly, that between input and the output when w is 0, w of t is 0, then again you can write it C 2 S I minus a whole inverse, then your B 2, then D 2 2. So, I can easily find out what is our that matrices. What is that one? These matrices we can easily find out from the knowledge of the state space equation of this one. Now, this is this one. So, now I am writing it what is Z. Z is the represents Z represents those output of the system whose dependence on W of t. For example, I told you states, for example, states, error signal, and controlled, mind it is not a controlled signal, controlled signal, the signal which we are going to signals control, and that are dependent on W, effect of W on Z, we will consider this, and this is the measured output, which will be used for designing a controller or generating the U of t. And this we have written, this is the control environment, and W is in general, W is the exogenous input, as I told you, exogenous, that we do not have any control, that noise, disturbances, disturbances and command inputs, that we do not have any control. So, this is the any system, now short, any system we can represent into a 4 block diagram representation. This is the block, 4 signals are there, input output, 2 outputs are there. In general, I can represent in this one. If there is a perturbation is there, additive perturbation, we can take it out from the plant model, and the controller is this one. So, this is the general structure of the, we know how to find out that one. Now, next question is, if you want to merge that, you see the, if you want to merge the perturbation block, this is called perturbations block, perturbation block. So, this is can call upper loop of P, this is the PM, upper loop of PM, agree. So, this if now if PM of S and plant uncertainty, if you want to merge together, PM and delta you can merge together, then how you can do it? If the plant PMS and plant uncertainty delta A are combined to give P delta of S. Now, how to do it this one? We know this expression Z y is equal to P 11, P 12, P 21, P 22, W and U, and also we know that W is equal to delta A Z, and delta A perturbation block, which we can place it in diagonal form, all perturbation in the elements we can put it in diagonal form. So, now I can write it Z is equal to P11 W plus P12 W one expression, y is equal to P21 W P22 U. Now, from this eliminating W, from this expression eliminating, how will we eliminate W? W expression I can put it in terms of Z, then I can express Z in terms of U. Agree? So, that if you express Z in terms, let us see how to eliminate the eliminating W from Y expression. That Y expression. First thing we can write it Y is equal to P21 W. What is W? ZA, delta A into Z plus P22 U. Agree? So, what is Z? Now, what you can write it? This Y delta A this. So, Y is equal to now and another expression I know Z is equal to what? Z is equal to I know P11 delta A Z P11 W. For W I am writing delta A Z plus P12 U. So, Z is equal to bring it that side. Agree? So, I can write it I minus P11 delta A whole Z is equal to P12 U. So, Z is equal to I minus P11 delta A whole Z. Now, one can easily find out the dimension of P11 from the basic equations. Immediately you can find out that what is the, it depends on the dimension of this one, depends on dimension of Z and W similarly. So, number of inputs is in this case number of inputs is W and not number of inputs is W and W dimension if you specify and Z is the measured output whose dimension is known. So, I will know the dimension of P11 as. So, so now I can write it in place of Z, put this one P21 agree P21, then what is the delta A, then Z is what? I minus P11 delta A into what is our Z? Sorry, it is not a Z, it is a U. So, this is our P21 delta A agree, then this just a minute. This is your, because you see I am taking the inverse both side this one. So, it will be a P12. So, there will be a P12. So, P1 to this delta A as it is Z I have expressed by that one into that is U is already there. So, you have a U plus P22 U. So, if you now take it common, so P22 plus P21 delta A I minus P11 delta A inverse P12 then U. So, now you see how to remember that one. When you want to make the outer upper loop, this is a lower loop, outer upper loop is delta A, outer lower loop is delta A. When you want to merge the outer upper loop block into a P, then input output relationship, input output relation y and u relationship, transfer function you are getting this. Now, how to remember? When you are putting the upper block agree to merge into this block, then you consider the lower part of this one P 22. So, P 22 the first index, second index P 22. So, first index will be there P index is 2 P 21 delta A, the perturbation we are merging, that delta A is merging delta A, then multiplied by I minus P 22 already consider what is left is P 11 is left, multiplied by delta A whole inverse. Then first index we have taken it P 21 agree, then this second index we have to take, second means second index. So, P 12 is the second index is coming, multiplied by u. So, this you can write it now block diagram form, if you see it, it is like this way P delta of S, this is W, this is Z, this is our U and this is our Y. You see the upper block of 4 block upper loop is merged and that is denoted by P delta A. So, this is nothing but a P delta S U of this, and now this is the controller. So, this thing, this whole expression we can write, it is a function of P and delta A U, and that is called, this is called L F T. This is called linear fractional transfer function, linear fractional transfer function. Transfer LFT, and since the upper block is merged to this block 4 block, it is called ULFT, ULFT. Since the upper block is merged to this one, it is called ULFT, upper linear fractional transfer function. Transformation or not transformation, transformation. So, this is called linear fractional transformation, LFT, linear fractional transformation. Since the upper block is merged, it is called upper linear fractional transformations. Okay. Similarly, one can do, if you like it, now you see the outer loop of the block is merged to the outer loop of the P block is merged to the P block. Now, one can do the outer upper loop, the outer lower loop can be merged to the P block, and that will looks like what? That will be looks like this. So, we will define between P k delta of S. Okay. So, tomorrow we will discuss this one, how one can do this one, and this is W and this is Z. So, this is a lower block is merged to the P block. So, it is called lower L F T, lower fractional transformation. The lower loop is merged to this one. So, tomorrow we will discuss the rest of the things. So, our main job is how to any system given is description, perturbation, noise, everything we want to represent into a 4 block representation, and it is analysis in transfer function domain.